Okay, thank you all for joining us this morning for today's O-REU seminar. Today we are very glad to welcome Professor Cynthia Hipwell, who will be giving us a seminar about friction and adhesion in the finger-device interface. So Cynthia got her PhD in mechanical engineering at the University of California at Berkeley. Your profile doesn't say when, so I'm going to assume that wasn't very long ago. Then Rice University is where she got her bachelor's degree. So she's actually a alumnus of Texas universities. Um, she is a member of the National Academy of Engineering, which is a big deal. So one of the highest honors that an engineer can, professional honors that an engineer can receive. Among other honors and awards, for instance, she is a fellow of the National Academy of Inventors, and then as of 2019, received a faculty mentoring award, which is a sign of her dedication to mentoring. So we're very happy to have you presenting to us today, and I hand it over to you.
Thank you, Michael. Let's see, is this little gray box kind of showing? Should I, oh, there, I'll make that small. Okay, howdy. I'm going to be talking to you today a little bit about friction and adhesion in the finger device interface. Let's see here. Just to give you a little bit of a background on what I do here. Actually, Michael was kind to say that my PhD was just a few years ago, but actually, I joined Texas A&M about 3 years ago after 21 years in industry. So you guys can do the calculations there on the PhD. And most of that was developing recording heads for hard disk drives at Seagate Technology. And particularly looking at the interface between the head and the disk. And that's kind of how I got interested in interfaces. So since I've come here, I've created the Invent Lab, which stands for Innovation Tools and Entrepreneurial New Technology. And we're really focusing on what I call that really interesting space in between the idea and the product. So, you know, maybe kind of think of this from the time in between kind of a first concept or maybe a first science or nature paper about your material to actually getting that into the product. And there's actually a lot of really interesting physics in that space. Physics that determine how reliable the product may be, physics that determine how manufacturable it may be. And actually, by understanding those physics, we can design products to have enhanced capability, to have reduced failures, to actually be more manufacturable. And so we're kind of playing in that space. My students get exposure to that. And so I kind of call it personal training for innovators. And you guys in materials science in particular, I think there's a very interesting space for understanding in depth those materials and then turning that into new products and features for the devices that are made of your materials. So some of the technical areas that we're specifically looking at right now, I have pivoted. So this gives you a bit of an idea of how someone pivots. When you pivot, you have one leg placed in place and one that moves, right? So looking at interfaces and tribology and contact detection and actuation in the head disk interface, I saw some need in the area of haptics and robotics. And part of that is because of its early days in haptics, and miniaturization and better understanding of the physics is going to be able to enhance those products. So we look at the tribology of touch for haptic perception, and that's actually what I'm mostly going to be talking about today. So I'm going to dig much deeper into that. We're also doing small scale MEMS device characterization in this space and looking at the tribology of robotic interactions, manipulation and locomotion. When the robot interacts the environment are heavily influenced by the friction and adhesion and understanding that in that space. And so being able to drive better control in robotic interactions can provide better performance. So what is tribology, in case you're not aware of the exciting field of tribology? The term was first used in 1966, and tribos means rubbing. So I guess if you were to do like a literal translation, that would be the science of rubbing. But today we really more call it the science of these interacting surfaces. And it's actually a really multidisciplinary field. You need to bring in physics, chemistry, all the math you've had, mechanics, heat transfer, fluids, materials, all of it. And so we've actually got a pretty strong group of tribologists here at Texas A&M, and they actually come from multiple departments, material science, mechanical engineering, chemistry, chemical engineering, and all come together to try to understand those surfaces at a very small scale. One of the things is that most of what drives what's going on at the interface is at a very small scale. So as we've gotten more and more tools at the nanoscale over the last 20 or so years, it's driven a much deeper understanding of what's going on at the interface, which allows us to engineer more in that space. In Vent Lab, as I mentioned, we're particularly interested in the tribology of the interface between fingers and devices. So like my finger and my iPhone. So why are we interested in that? I'll give you a little video.
When you think about it, the sense of touch is the one sense you can't turn off. You can close your eyes, you can close your ears, close your nose.
Can you guys hear that?
And yet you can't turn off touch, and yet that's exactly what we've done in the digital world, and we're here to change that.
So we've created a technology that allows you to feel what you see on the screen.
Oh, wow. Yeah. Oh, that's really cool. That's really clever.
Like, this sort of thing is really interesting to me. And I always think that's a sign of good tech. It's like, if this hadn't already happened, like, why has someone not done this already?
I definitely would want to see that integrated into my mobile device.
Well, we're redefining touch with the touch.
I'm just pausing for a second. Are you guys able to hear the audio of the video?
Yes, I can.
Okay, just making sure. I had trouble with that on a different one.
We're actually going to make it so that you can physically feel what you see. I can feel the clicks and all these different interactions. Oh, the applications are endless. Consumer electronics, gaming, advertising, retail, automotive, vision impairment. Anything with a touch interface, we can create a physical interaction. As we know, touch displays require you to look at the screen. And so while you're driving a car, it means you have to take your eyes off the road. What we can do is take you back 10 years ago when you could actually navigate your dash with a sense of touch. You can feel where those buttons are. And as I move them, I feel them physically click into place. And what's great about this is that I can keep my eyes on the road. Well, gaming is all about having an immersive experience. And that's why VR is becoming more and more popular actually in the game. But it's all vision-based. What we can actually create is a real physical interaction, just like in the real world.
Oh, wow. And you just follow the path and you feel it. That's really cool.
You've seen retail go from brick and mortar to now almost be exclusive online-based. And that has really suffered in terms of consumer experience because now all you have to know whether or not that shirt is good looking is from a picture. But what about searching through the sense of touch? How about the sense of textures? You could actually find a texture you like and find shirts that are within that category. Where I can feel those corduroys and feel how different they are to a pair of moleskin pants.
It does feel like corduroy. I don't know what moleskin is, but it feels good.
Retail is always looking for a way to give consumers a full experience so that they know what they're purchasing. And what better way to actually physically feel that sweater or that shirt. Well, our TAM is touch technology. It's going to be the Dolby or Intel of touch. We're going to essentially put our technology into any touch application so you can feel what you see on any device. Imagine getting a text from a friend, reaching for your phone and physically feeling a smile. Actually interacting with each other through the sense of touch rather than just sight and sound. So that text messages actually have this extra layer behind them to give you emotions. So it's essentially a texture emoji. Tanvis is the company redefining.
So a little bit of a promo for Tanvis, but that's the company that we are working with and how I got interested in this. Let's see here. So just in general, a little bit of background about haptics. So haptics is any technology that simulates the sense of touch and motion. And actually, even if it's not a technology generating it, like how your computer feels, how any product you have feels, the feeling of that is also referred to as haptics. And it's really considered crucial for the next generation of human machine interfaces, both because of, they identified NAE Grand Challenge of Enhanced Virtual Reality, so both for virtual and augmented reality. And then also just again, that the future of work, how is work going to change as we interact more with digital colleagues, with robotic colleagues, or even in ways that provide us more information with less cognitive load. Haptic signaling can actually help with that and be able to give us even somewhat subconscious signaling and messaging. The market is very significant. It's projected to grow to 22 billion by 2023. It's got a significant compound annual growth rate. And this is because it's increasingly being integrated into your mobile phones, tablets, gaming, automobiles, your wearables. As you already have haptics to some very immature degree in your phone, in your iWatch, and then very importantly for virtual and augmented reality, for something to be perceived as real, it needs to engage more fully the senses and not just be audio and visual. And so if you do not feel it when you interact with it, it's not going to be considered a completely immersive experience. And you may be experiencing that now as you're talking to me and do not feel, or listening to me, I guess, and maybe not feeling completely present in your virtual interaction. And can we bring touch into that space? Surface haptics is actually what the Tanvis technology is based on, and it just means that the haptic effects are on surfaces and most commonly touchscreens. And that particular part of the market is the fastest growing piece of the haptic market because of the ubiquity of the touchscreen. And there's actually a lot of need even for things such as modifying touchscreens to be ADA compliant. You may notice that you don't have a touch screen when you go to a retailer. There's still physical buttons, and that's to be compliant for people who are blind. And so being able to get that tactile feel back into touchscreens will make touchscreens also much more accessible. So it's clear that surface haptics are a big deal, but why do we care about the tribology in there? Mostly it's because that those haptic effects are actually driven by friction and vibration. And so when you are feeling something, at least the tactile portion, so there's tactile and kinesthetic. Kinesthetic is like that your hand stops moving when you interact with something else, but the tactile is the smaller scale feel. And that's driven by changes in friction and vibration, and that the interface between the finger and the device is very complex. As I mentioned, a lot of this tribology is driven at the very small scale, not only the mechanical properties, but the geometry at that scale. More macroscopically, you can see the geometry of a fingerprint. But that's actually huge compared to the texture that we care about at the very small scale. You've also got the chemistry of the interface with the sweat in the interface, the sebum, which is the oil that's on your face and skin that is also in the interface, and all of that. In addition to the properties of the device are driving what's going on there. When you're talking about making a high volume consumer electronic product, you're not just talking about demonstrating something a few times. You need to have it be very consistent. And if you need to put in features to accommodate the variability, it can be more expensive. So if you can better understand what's going on, design products to be insensitive to variability, they can have increased performance and you can actually drive down costs. And so you want this device to be able to work in all humidities, all temperatures, with all types of people. Skin can vary greatly by age, gender, how much somebody sweats actually. And so all of this, you want your device to be very insensitive to those effects. How did I get interested in this topic? I actually ran into the guys that started Canvas at a haptics conference. They actually started the company based on PhD work that they'd done at Northwestern. And I got sucked in because this kind of looks like a disc and a disk drive, actually anything that's an aluminum circle with diamond-like carbon on it kind of sucks me in, looking like a disc. So I started talking to them about their device, and they were looking at different materials and structures. And I thought this was showing the force that they got versus the current. And I thought, oh, this is great. They must be getting better performance out of this diamond-like carbon coating. And they said, no, actually, they cannot use that for their product. And that's because of this band here. And this is the variability. And so even though they got a much larger effect, which would be very desirable to be able to lower the high voltage electronics for the device, they could not accommodate that variability. And I started talking to them about ways that you might be able to design that out. And that's kind of how the collaboration got started, is thinking about, can we design the surface to preserve that high electroadhesion effect, but reduce the variability? So what we're thinking about, again, is increasing that nominal effect, the main effect that has been modeled and they're designed for, but decrease the sensitivity to variables such as humidity, sweat rate, and finger properties. And so we had the hypothesis that this might involve not just the electrostatic effect that electroadhesion is based on, but that there's a lot more going on in the interface, including adsorbed water. There's always a thin layer of adsorbed water on interfaces from the humidity in the air and the sweat that may be on people's fingers. And so could we, if we decreased the capillary effect, could that potentially reduce the variability? But for screens, anything we want to do, we do not want to be visible. People do not want to see, no matter how cool the tribology is, no one wants to see their texture on their screen. So we need to be looking at this at the nanoscale. So it's going to be below the wavelength of light and therefore not visible. So if you start to look in more detail at the tribology of the finger device interface, there's a lot that needs to be considered. So we've got, here we've got our skin. The skin actually has multiple layers with different properties. So the outer skin layer, the stratum corneum, that's most in play here, is actually a fairly stiff layer. And then as you get into the deeper layers of the epidermis, then you get more viscoelastic properties that need to be considered. But you do also have property changes as that stratum corneum becomes moist. So we need to consider changes in property, both due to sweating and due to humidity. We have the actual texture, structure, and macroscopic structure of the fingerprint. We have these capillary forces that are coming into play, capillaries that are forming between the texture of the device and the texture of the finger. We have the device properties, both their mechanical properties and their electric properties, because we have a transparent conducting layer of indium tin oxide here, a dielectric layer, and then this volt that's applying a potential to the skin. And that how the electroadhesion works is it's actually kind of like two parallel plates just pulling the skin towards, or the finger towards the device. And as more and more of those little skin asperities get into contact, there's more area in contact. And so that is causing a higher level of friction. So they start out with a low friction device and they pull more of the finger into contact, and that increases the friction. So we need to be considering all of these aspects when we're modeling and designing the interface. Oh, and surface energy as well, as that's going to impact how these capillaries are actually interacting. So experimentally, we designed a custom tribometer for this because we think that the sweat and chemistry of the skin is actually important. We are not using an artificial finger. There have been artificial fingers designed, but they don't actually include the sweating aspect of it. And so we actually do our experiments with student fingers. And we have IRB approval if anybody's worried about that. And have designed this tribometer to measure the friction as the hand is swiping. We actually swipe the screen and keep the finger constant. We also have a vertical stage and a control loop that keeps the normal force constant. It's actually pretty difficult to have a person keep their normal force extremely constant. And so then we have the tribometer will scan, simulate at the speed of a swipe, and will measure the friction while we have the electroadhesion applied, while we don't have it applied. As I mentioned, we have this vertical stage for constant normal control. This will kind of show swiping back and forth, how much the red is the amount of normal force control just the person has. And you can see that there's much better control when you've got that stage actually keeping that force constant. We also have an environmental chamber to control the temperature and humidity to be able to look at the variations for these environmental conditions. And as I mentioned, we actually use the electroadhesion screens, so we have the ability to drive different AC signals into there to simulate the different textures that they might be simulating on a canvas screen. So we did, just to start out, look at the effect of friction with humidity and changes in applied electric field. So we have our friction force, our humidity, and here we have change in friction force. So the blue is just with 0 volts. And so you do, from that capillary effect, you do actually have increasing friction between the finger and the device, even without the voltage applied versus humidity. And then looking at what happens when you actually add 100 volts and 150 volts. And then this change in friction is actually what matters for the feeling that you'll get. And so look at that versus humidity as well. And what was interesting is that we weren't just seeing the expected changes in friction with the humidity. We're also seeing changes in the electroadhesion with humidity. And so started digging into that a little bit more. What is going on there? What is that due to change in properties? Is that due to electrowetting? And so started to investigate the electrowetting aspect a little bit more. and recognized that our hypothesis that the capillaries were important was likely true, and so actually developed a full model of this, including the capillary forces. And so we got the geometry of both the glass and the skin texture on a very small nanometers scale. Then actually modeled the deformation during contact. We also modeled the water distribution to be able to look at where the capillaries would form, and calculated the capillary force out of that. We're also in the process of looking at the dynamic aspect of that, looking at the contact angle hysteresis that you get as the capillary is moving. We also looked at electrowetting on the electroadhesion glass. So actually putting DI water on here, I'll show these little dynamics. You can see as we add the voltage, you see the electrowetting, the change of contact angle more towards wetting with voltage. This is, DI water on a very clean surface. Realistically, the water in the interface is probably closer to sweat. So we did look at salt water on a clean surface. The effect was, this was a concentration that was similar to sweat, and the effect was pretty significant. And then also looked at DI water on a rubbed surface. So now you've got the surface energy changed from buildup of sebum in the interface as well. And so that was also very, very significant. And so we realized that this was probably part of what was going on as we have applied the voltage and we have the capillaries in the interface. And so we actually calculated the amount of force generated from that purely electrostatic force and compared that to the electrowetting. And we actually showed that the amount of force that you'd predict just from electrowetting would be of the same order as the amount of force that they were predicting based on purely electrostatic arguments. And so at this point, capillary force needs to be considered, and electrowetting needs to be considered in the design of the interface. So how could we use this to improve the design? Now we know that this is playing a big part. It's probably contributing to the variability. How could we use that to improve the design? So one concept really came to us from looking at the influence of asperity shapes on capillary force. And so this work that had been done looking at the effect of different types of shapes of asperities as they, the capillary force as they, at different humidities. And so something that's interesting about this is if we want to design out the capillary variability, we might want something very much like this constant low force with humidity, and that would be in this little trapezoidal shape here. So we started looking at, can we texture the surface at a small scale? To start out, we had samples that were textured that Tambus was looking at. And so we actually looked at a pretty shallow texture through to a deeper texture. So this is all formed, same company, same design, to be able to look at, can we make it less sensitive to variation with humidity? And so we have the 3 different designs. The red is sample 1, and you go down to blue is the deepest texture. So we still see, an increase in friction with relative humidity and some change as well as change in friction force with relative humidity. Something that's interesting is that perception has been shown to be this delta friction force over the initial friction force. And so if you plot that, we can see that we can get a pretty constant delta friction force over friction force with that texture. So there's definitely the potential to reduce that sensitivity to humidity with the textured surface. Now, the question might be, do you with how strong the electrowetting force is, do you want to do that, or do you want to design something that kind of trades off between the two? But that's another design question. So at that point, those are the two things we're looking at. Can we actually look at specifically designed texture shapes, such as that concept shown a couple slides earlier? And also going the opposite direction, considering how strong that electrowetting effect is, can hydrophobic surfaces increase the range of angle change and the magnitude of electrowetting? How might that be used to enhance the effect instead of trying to suppress it? So looking at both of those currently in my lab. The other thing that has kind of spun off from this, outside of just the electroadhesion, is looking at the impact of these nanotextures on how things feel in general. And what got me thinking about this was that we had two different glasses from the same supplier, and they were actually different gloss levels. They were made for their optical properties. These are glasses that are intended for screens, and so they're made not to have sparkle, but also to feel, they make them to feel pleasant. But these two different glasses felt really, really different. But then once we got them under the atomic force microscope, they look less different than we expected. In fact, if you model the finger interacting with these asperities, the finger doesn't deform enough to actually touch the bottom of this glass. And so if you just look at the kind of top 200 nanometers where the finger interacts, so like kind of truncate this more textured one to the finger from a contact area perspective, from a purely contact mechanics perspective, these glasses should feel almost exactly the same, yet they feel dramatically different. And so we're thinking that this capillary and possibly even some heat transfer aspects of it are influencing what's going on in the perception. And just showing this is kind of that concept, is that at that higher level, these two textures look the same. And so we did model the contact process for both of these. And the contact, again, going into even far beyond the level of pressure that you would ever put for your finger on this glass, the contact area between these two is very, very similar. So then we looked and modeled the capillary difference, because if you've got taller asperities, that's going to stretch out the capillary and reduce the capillary force. And so we are seeing, again, this is showing that accumulated cross-sectional area, where the area at the bottom, where they never get to, where you almost never touch, is the only difference. The contact area at the top, well into until you touch the bottom of these materials, is exactly the same. And so that ends up making them have a very similar contact area from a contact mechanics point of view. But the capillary force between the two is significantly different. So how does this impact the design of products like the glass? And it kind of starting to look at this introduced us to a whole new world that we didn't know people did, but they do. There's actually a lot of effort put into how products feel. So glass designers, packaging designers, we've talked to people down at Dow Chemical Packaging, we've talked to glass suppliers. You know, Apple obviously does it for its products. Consumers actually judge the desirability and the expensiveness of products based upon touch. And so, as an example, Dow designs the organic pasta packaging to feel more expensive, whatever that means, feel more expensive than the regular pasta packaging. And right now, they do that through a trial and error approach. Basically, they shoot different nanoparticles at the packaging and they send it up to lab and they have people feel it. And so they try different things and they feel it and they decide the one that people like. But if we're starting to understand what's happening, the mechanics of what's happening in the interface, can we relate different levels of contact area, wetting, thermal properties, and predictively design packaging, products, glass, devices to feel a certain way for consumer products? And so that's actually a direction we're going with the current proposal, to be able to create tools that can predictively design those products. So that is the end for right now, leaving you guys with lots of questions because you're scientists and want you to think about it. I do want to acknowledge the students and postdocs in my lab who do all of this amazing work and make it super fun and interesting for me. I also want to acknowledge Canvas. Obviously, we've enjoyed a really interesting collaboration with them. Also, Dr. Jonathan Feltz, who is looking, I didn't show it today, but looking at some of these effects on a very small scale with an AFM, and acknowledge support from the Governor's University Research Initiative, the President's Excellence Fund, my startup, and Mr. Holly Frost. Questions?
Thank you very much, Cynthia, for this very interesting and engaging talk. If you have questions, please unmute yourself and ask it to the group.
Dr. Hipwell.
Uh-huh.
This is Christopher Wheatley from TAMU. My question was more on the side of, I guess your industry experience. When you're working with these different companies and working on putting this research into an actual market, what lessons and what do you usually have to teach and work through? What are the biggest challenges in dealing with kind of the research environment and academia, that sort of environment, and actually moving and pushing that product to an actual physical market and industry?
So part of the reason that I like to work in this space that I do is I actually think a lot of the types of problems we're working on with Canvas right now, I mean, they are actually a company that's moving their university research into commercialization, right? And so when you actually try to take something to high volume, that's when these small effects that might be a 1% effect or a fraction of a percent effect can start to have a really big effect on the performance of your device as you ship it in volume. And so that's where us digging into some of the science of what's a variability, the science of full environmental conditions can be very interesting. Where I didn't include it in here, but we're actually working with them on some interesting things around how the electric field interacts with contamination in your finger. And so actually those type of challenges and thinking about what could go wrong, not to be a I guess, a Debbie Downer, but to actually be a solution provider of thinking about ways that the device could fail, about ways that the device's performance can be enhanced, and figuring out ways to do that. I think not everyone thinks about those things because they want to be optimistic about their device. So thinking about how you get your device into a full volume production and reliability level, I think is a big challenge to think about. But I personally think it's a very interesting space.
Thank you very much.
Mm-hmm.
Hi, thank you for your presentation. I had a question. You mentioned at one point the surface energy of the skin has different effects. Can you explain that a little bit more?
Well, so the contact angle of the capillaries is going to be determined by the surface energy of your skin and the surface energy of the device. And so when you have a little droplet, the energy which is actually going to determine how that's the balance between the surface tension of that droplet and how that's going to form and bond to with the forces, van der Waals forces to the surface. And so if you change the surface energy, then that's going to actually change the angle that the droplet or the capillary actually form at the surface. It changes the balance of forces, and so it'll change the shape of the capillary. Does that
makes sense? Thank you.
So I had a question. I understand, of course, that the majority of the commercial applications for these kinds of screens would be in our sort of usual human environment, rooms, streets, the kinds of places where we spend most of our time. But I imagine that one niche application may be in underwater environments, right? So you might have things that go into places where people are diving, or or into swimming pools or something like that. In that case, the environment for the screen changes completely, because now you're not looking at sort of little capillaries of water forming in an otherwise air-filled environment, but you're looking at a water-filled environment. So would the physics of that of that interface and of the touch process change appreciably if you were to try to create a screen to act underwater?
It would. In fact, this design probably wouldn't work because you wouldn't get that gap. The water would be too conductive, and you wouldn't get that capacitive gap. In fact, they do find that people who have super sweaty hands actually have some difficulty with the screen. So you're kind of almost, it's not, you've still got the dielectric layer there, but it's almost kind of like a shorting out of what's happening, and you don't create that capacitive gap anymore. So to do an underwater screen, you would actually need to look at a different design. There are touchscreen designs for surface haptics that actually vibrate the whole screen. And so what they're doing is instead of this one starts out with a low friction screen and increases the friction with the electroadhesion process. The other design starts with the high friction screen, and then as they vibrate, the vibration actually reduces the intermittent contact, and that you're actually getting kind of a little mini air bearing lubricating in between the finger and the screen that creates a friction reduction. So you could possibly do that, but then the challenge would be starting with the high friction screen in an underwater environment, because the water's already lubricating the environment as well. So you probably have to design the screen to be kind of grippy. And that would be an interesting challenge in itself. It actually would be pretty cool to try to design that. Other questions?
Yeah, hello. Thank you for your presentation. I was excited to see this because I'm taking a class in tribology in the fall.
Oh, excellent.
Yeah. So I'm interested in MEMS devices mainly, but I wanted to ask if how the electrowetting and capillary effect happen in MEMS devices. If you have any information on that.
So actually, capillary, even without the electrowetting, is extremely important in MEMS devices, because when you go to the smaller scale, surface effects and smaller scale forces, such as those formed by capillaries, become on the scale of the other forces that you're looking at. And so in the early days of MEMS, one of the most challenging problems was actually that the little cantilevers, once you'd fabricate them in the fab, as you rinse out, once you etch and release them, and you rinse it out with water, as it dries, the capillary force from that receding, drying capillary would actually pull the cantilever down and make it stuck, so that it didn't allow the motion. And so capillary forces definitely need to be considered in MEMS devices. They can actually, but that actually means they can also be used in MEMS devices if you actually design in water into the system, or another fluid or liquid into the system. It can actually be used as a pumping mechanism or a fluid motion mechanism within MEMS devices. So it's actually extremely important in MEMS devices. And I have not looked into enough on if people are using electrowetting to draw as a driving force, but it would definitely be a potential driving force, especially in microfluidic and kind of lab on a chip devices. So
Great.
enjoy your
Thank you.
tribology class and your MEMS.
Yes.
Anything else?
Oh, sorry. I guess now you can hear me. This is Dilma.
Oh, yes.
Yeah, hi. So I'm the ignorant here in the group because I never heard of tribology, and I really, work on another level of the technology. But one of your slides had healthcare as one of those, and I think that even in our NMED program, seems to me that there are a lot of things that we can do for neurologists so they can have virtual consultations. Because if you go to a neurologist and they keep asking you, do you feel this more or that more, this or that? There's a lot of perception that I think that one interface like that, really be able to give more. It would help humans to actually express more by varying, the texture, things like that, instead of the kind of, it seems to be primitive way that we do things these days. Another, kind of observation is that a few years ago, Facebook was investing a lot on a lot of things that would allow to have devices that would extend the perception of people when they are using Facebook and things like that. And they do, I believe, made a lot of progress in being able to communicate things through the skin, so that you could learn what is going on Facebook without having to take your phone. I don't know why would anyone want to do that, but I do understand that there is value in communication that is not visual for a lot of people. So there's, you know, another spirit. And just for the other colleagues and students, besides this line of work in the college, we also have the electronic nose, right? We have the device that you can put in your cell phone that you can recognize the smell. So these researchers work in that area. They take that device to cheese identification of cheese electronically. And you take this device, and the device will say what kind of cheese, Gouda, blue cheese, Gorgonzola, whatever it is. I know that the researchers working in that area, like there is Gutierrez in computer science, there is a couple electrical and computer engineering. I think that there is also an intersection with the kind of work you're doing on another level. Again, trying to expand. So that, you know, overall, I think we are giving TEAS in our college, you know, a lot of ways of expanding the way of using devices. So this is all very cool. Thank you for your talk.
Yeah, you're welcome. I think there's a lot of opportunity here at Texas A&M, given the expertise we have in materials, in computer science, in visual, you know, even connecting with the visualization and trying to bring touch more into visualization. So I think there's a lot of opportunity to make connections here and expand it at Texas A&M for sure.
I agree.
Okay.
So I wanted to thank again Professor Hipwell for this presentation. Thank you all for coming as well, and we look forward to seeing you at next week's seminar.